So in question 9, per usual, we are given some data, given a nice diagram. So as we're reading through, let's start copying out some of this data and defining it to equal variables. So we have a car of a mass 820 kilograms. M, let's say, equals 820 kilograms. It is travelling at a constant speed of 32 meters per second. V equals 32 meters per second. It's travelling along a banked track. The track is banked at an angle of 20 degrees to the horizontal. Let's say that theta equals 20 degrees. Part A. The net vertical force on the car is 0. What this is saying is that the weight and whatever is upwards here, the reaction in the upward sense, is equal to 0. We have to be careful because usually when we're greeted by something like this, we may be tempted to then just think, oh right, we're going to convert, we're going to find out the components of the weight that is perpendicular to the slope and the weight that's acting down the slope parallel. However, we're not told that the weight perpendicular is equal to the reaction, so we have to be careful in this one. Instead, we're having to split the reaction force into its components to find that R upwards up here, that would be equal to the weight. So let's work this out then. Let's say that we must have, let's break the reaction force into its components upwards. We know that this angle here, by geometry, would equal 20 degrees. And so then, if we say that R cosine 20, cosine because it includes the angle, we're bothered about this component acting up here, R cosine 20 must be equal to the weight, because the sum of the, if we do R cosine 20 minus the weight, that would equal 0, as we're told the net vertical force is 0. And so all we need to do here is think that, well, the weight can be said to equal mg, so we could plug that in, divide both sides by cosine 20, we'd then get that R equals mg divided by cosine 20. And let's input our values here. We would then have that m is 820, 820 times acceleration due to gravity of 9.81, all divided by the cosine of 20. And if you were to do that on your calculator, you'd get a value of 8,560 newtons, and that's been quoted to 3 significant figures. And lo and behold, that is equal to 8.56 kilonewtons. So 3 significant figures. Part B. We're now asked to use the answer that we've just calculated to calculate the radius. Well, we were dealing with forces here. We're told about something to do with a radius, we need to find the radius, and we know an equation that involves the force and the radius when it's got to do with centripetal acceleration. We know that F is equal to mv squared divided by r the radius. The centripetal force then, well, what is providing the centripetal force in this case? Well, when we have a look at this, the only force acting in the direction towards the centre of the circle is a component of r horizontal. So then we can say that this centripetal force is then equal, is being provided to the component of R to the horizontal. Well, that component would be big R, the contact force, and then that would be times the sine of 20. Sine because this component here excludes the angle 20. This is the same as R times the cosine of 70 degrees. It's the same thing. I just like to work with the same angle though. So then all we need to do now is make the radius little r the subject. We know what the mass is. We know what the speed is. We're given it earlier on. So let's just make r the subject, times both sides by little r, divide through by big R times sine of 20. We then get that little r equals mv squared divided by big R sine 20. And let's bring that up here. Inputting in our values then, the mass of the car is 820 kilograms. Speed is 32. I have to square that. And that's all divided by the contact force R, 8560. I'll do ... there to show that I'm using an unrounded version. And that's all times. That's times by the sine of 20. And plug in all of that into your calculator, you'd get a result of 287 meters. And that's been quoted to 3 significant figures there.